Alright, to finish up these mass spec questions, we have one here that was an old diploma question that's a released item. And this makes use of the direction prompts you'll see here, also very common on the diploma these days. So let's read the context box and see what's going on. So we have a positively charged particle, or ion rather. It travels through a region that contains perpendicular electric and magnetic fields, and the ion passes through the region undeflected at constant speed. So before we touch anything, let's dissect the problem. First of all, positively charged. If we're doing anything with hand rules, this is going to be the right hand. And that's the first big trap they're trying to get you on, because we're so used to dealing with negative charges, we want to use that left hand. In this case, we're going to use the right hand. It's telling us the electric and magnetic fields are perpendicular for everything in Physics 30. That should be expected. And now we have the ion, it passes through the region undeflected at constant speed. So this means FM and FE are balanced, or they balance each other. Right, so we have our two plates. We have our negative plate up top and our positive plate on the bottom. And then we have all these nice little direction prompts. So it's going to ask us to match those numbers with the descriptions. So it's asking for the direction of the electric force, the direction of the electric field, the direction of the magnetic force, and the direction of the magnetic field. Alright, so first thing is, let's draw a free body diagram for this thing. So here's my lovely little point particle. Now, we're told that this is positively charged. So because it's positively charged, we want to ask ourselves, at least in terms of electrostatics, which plate would this most likely be attracted to? Since it's positively charged, it's going to be attracted towards that negative plate. So we're going to say that there's an electric force going up. Now, at the same time, because we're told this travels through the region undeflected, that means we have to have that FM counterbalancing that, or it's going to go down and it's going to have the exact same magnitude. And that's important. If we want that to be undeflected, we need those forces going in opposite directions because we want that net force to be zero. Right, just doing that, that takes care of two of the four blanks. So looking at our diagram, we know that Fe is going to go up because that positively charged particle wants to go towards that negative plate. So the direction of my electric force is going to be up. Based on my arrows, this is going to be a 5. We'll deal with the electric field in a minute. You don't have to do these in any order. And then the direction of our magnetic force, it's going to go down. And then we're going to use a number 6 for that. Those two blanks, the first and the third, those are meant to be kind of the quick, easy ones to get done. It's the second blank that's slightly harder, and the fourth blank, that's where most people get messed up. So this one's asking about the direction of the electric field. Well, in a parallel plate configuration, the electric field always travels from the positive plate. It starts on the positive plate and it terminates on the negative plate. So in this case, our electric field will be going from bottom to top here. So it'd start on our positive plate and it'd work its way up to the negatively charged plate. So this electric field is going to have a direction of up. We're going to have a number 5 here. The last one's the direction of the magnetic field. A lot of people get magnetic force and magnetic field directions mixed up, or they think they're the same thing. They're not. They're related, but they will always be perpendicular to each other. So this is really important. These are always perpendicular to one another. What we should at least examine is what we have going on, because to find that direction of the magnetic field, that's going to require a hand rule. Now in this case here, we have the path of the particle. It's going to the right. So we know the speed of the particle, call it v. And we know that the magnetic force is going down, kind of using our free body diagram from earlier. Now again, where they're trying to get you is the hand rule. This is positively charged, so we want to make sure that we are using the right hand for this one. We want to find where is the magnetic field going. So with my right hand, I have to have my open palm facing downwards, and I need to have my thumb pointing to the right. Well, the only way to configure your hand in that fashion, to have your palm pointing down and your thumb pointing to the right, The only way that's going to happen is if that your fingers, they're coming out towards you or they're out of the page. So in this example here, we're going to say that the magnetic field is out of the page. So based on my direction prompts here, we're told that out of the page is a 0. So the last thing is we're going to get 0 for that direction. So the answer to this question for numerical response is 5560. The first 3 blanks, if you pick the wrong hand, if you use your left hand, you'll likely get these right. Where you're going to get this wrong is the last blank. If you used your left hand instead, you'd end up finding that the field goes into the page. So when you're doing any of these questions with hand rules, make sure you're paying attention to which hand you need to use. Pay attention to the polarity of the charge, whether it's positive or negative. That will affect things when you're dealing with magnetic fields and magnetic forces.